marine environment can be problematic, but they have also carry some important information about the seafloor. Thank you. So this is my this is our group member. We have my advisor and our member in the lab also have Dr. Bell from AGL Kinetic. And this is the talk outline. First, I'm going to talk about the guided wave phenomena and their properties. And also, I'm going to talk about the data we acquire in the physical modeling lab. And then I'm going to show you how we extract the shear wave velocity of the guided wave. And then I'm going to show you how can we get rid of this problematic guided wave. So this is a typical scenario that we acquire seismic data in the shallow water marine environment. If we have the towed streamer, we probably have these multi-path reflections. And they probably interfere with each other and form this very strong amplitude guided wave. And also, in the sedimentary, the interface between the water and the sedimentary, we are going to have another dispersive, which is shelby wave, and then they are going to can receive in the ocean bottom sensor. And also because the ocean bottom sensor have part of them in the water, so ocean bottom sensor also can receive this guided wave. And in the short guided wave will looks like this strong amplitude fan have a maximum group velocity boundary and a minimum group velocity boundary. And inside this fan, we have all these different phase velocities, and they have relatively strong amplitude and then other refractions and refractions. So guided waves are dominated by this simple equation. In this equation, we have frequency. This is the wave number, and we also have the water depth, the phase velocity, and the sound wave velocity of the water, and the mole number, and also the P wave velocity with lambda, and this is the shear wave velocity of the seafloor, and also we have the density. So from all these properties, we can distinguish these guided wave curves, and because we have this mode number, we can plot different modes in theoretically. So based on this model, we can plot this guided wave. We can see that this red dashed line are actually the boundary between the normal mode and the leaky mode. So the above this dashed line are our normal mode, which is the primary energy of the guided wave. And on the top of this dashed line are the leaky mode, which part of them are the shelby waves. And our focus is the more normal mode of the guided wave. So to examine the different properties of the guided wave, we plot this only one mode of the guided wave, and we change different properties parameters in the guided wave equation. First, we only change the P wave velocity and fix the shear wave velocity. So in essential, we are changing the P wave shear wave ratio over here. We can see that if we change the P wave shear wave ratio, the guided wave curve doesn't change very much. And also we change the density and fix other parameters over here. And we can see that the density curve also not sensitive to this density. And also if we change the water depth and fix other parameters, we can see that the guided wave curve are pretty sensitive to this water depth. And if we only change the shear wave velocity of the seafloor, the guided wave change very much because the upper boundary are actually dominant. The upper boundary of the guided wave are actually dominant by the shear wave velocity. So from here we can see that the guided wave curve are actually sensitive to both water depth and also the shear wave velocity. But in the field, we can actually acquire the water depth pretty accurately from the bathymetry survey, and also because it is shallow water environment, we can acquire the water depth pretty accurately in other ways. And to test our thought, we acquire our guided wave in our physical modeling lab. We build this model. We use this aluminum block because it's pretty similar to the hard seafloor, such as basalt. And we use the spherical source as the spherical transducer as source, and also this receiver move away from the source. So it's a two-way 2D survey line. And the offside is 3,500 meters over here. And we test two different water depths over here. One is 45, another is 100. And we acquire these two shot gathers. One is a 100 water depth, and another is a 55-meter water depth. We can see we acquire pretty strong guided wave over here, and it have a upper boundary of the minimum group velocity and the lower boundary of upper boundary of maximum group velocity and the lower boundary of minimum group velocity over here. And if we transfer these two shot gather into the phase velocity and the frequency domain, we got this different guided wave mode over here. And we also can calculate this guided wave because we already know all the parameters in the lab. So we can calculate this guided wave curve theoretically and overlap these different curves with our experimental data. And there are several interesting facts over here. So first of all, obviously the theoretical calculation fit with our experiment data very nicely. And also, most of the energy are concentrated in this frequency band because that's our source. And also, we can see that as I said before, the water depth actually dominant the mode number. If we have a deeper water depth, we have more modes. We have shallower water depth, we have less mode over here. So because the only one unknown factor in the guided wave is the shear wave velocity. So we can actually extract the shear wave velocity here and from the guided wave, because other like P wave velocity and the water depth and the density we can actually estimate from the shot gather. Because P wave velocity we can measure the slope, and the density we can get it from like empirical equations. So we can use this least square method. So this is our estimated shear velocity over here, and this C data is the phase velocity in the guided wave that is in the data. And we can also pick this frequency from data. So in the dispersive curve, we have both phase velocity and frequency over here. So we can input this peak data of phase velocity and the frequency and input into this equation, and get the minimum difference between our theoretical calculation and the real data. So from here, we can actually extract the shear velocity. And this is our least square fit. So the red dots are our data from the experiment or from the physical modeling. And these black curves are our theoretical calculation with our extracting shear wave velocity over here. So when the water depth is 100 meter, we have this one. And when water depth is 45 meter, we have 3181, this velocity. So the difference between these two are not that much. And if we examine the residue of this zero wave extraction, we can see that they're pretty small. And this is the error bar of our extraction. And also we do the direct transmission of the block. So we can see the direct transmission of the block is 3158. So they are not that different from our result from extraction. So consider the error of the measurement. So we can say that our extraction is pretty accurate, is reasonably accurate. And also, because we can extract our shear velocity, now we are going to think about how can we get rid of this shear velocity, this guided wave from the shell gather. We transform our shell guided wave into the FK domain, which is this, which are this blue curve over here. And in this FK domain, we also plot the P wave reflections, which are over here. And also we plot the convert refraction, which is the secondary hyperbola over here. And also we have this normal mode, which is the blue curve, and also the leaky mode is this red curve. We can see that if we want to require the multi-component data from the seafloor, the guided wave, which is normal mode, are overlapped with our converted wave over here. And if we consider we want to get some information in the low frequency area, the FK filter cannot separate the guided wave from other events very well. And also, if we consider in the real data, this is actually from the physical modeling data. So we consider the smearing effect of this spectrum. It's pretty hard to separate all these different events from here. So we think of this problem in another way, because we can extract this shear wave velocity of the guided wave, and we already know other parameters like a P wave velocity, because it's actually the curve is not that sensitive. So even though the P wave velocity estimation is not that accurate, it doesn't affect this curve very much, and also the density. So we can calculate this guided wave curve over here, and then we also have this real data. So we can mask this guided wave curve over this data, and give it a negative amplitude, and by this way we can get rid of all this guided wave curve over here. So as a result, this is our result of a guided wave filter. Sorry. So this is before the filtering. So we can see the pretty strong guided wave, and after the filtering, we can see that pretty clear the refractions of here. And also, if we apply this filter to 100 water depth over here, we can see that the strong guided wave fan disappear in here. So right now, I'm going to draw some conclusion to wrap this up. So guided wave is a big problem for our shallow water marine data. It can obscure our events like reflection and refractions. And also, the guided wave are not that sensitive to like a P wave velocity and the density, but it's very sensitive to shear wave velocity. So we can actually extract the shear velocity from the guided wave. And also, physical modeling can acquire quite perfect data, and they fit with our theoretical calculation very well. And extracting shear wave velocity of the seafloor works very nice, and use this extraction, we can actually create a filter to attenuate all these guided waves. And now I want to thank to the Geokinetic for support this program all the time, and also Dr. Bob to help me when I have some problem to write the program. And also Anoop helped me in the lab, and also Anoop that we have some interesting discussion.